Good afternoon, everyone. It is a great pleasure to be here. I have to start by thanking the many people who make this talk possible. I thank you, Meredith, Dean Tomiko, Rebecca, Jess, Sharon, Carolyn, and the entire Radcliffe family for making academic heaven a reality. I need to thank the sponsors of my fellowship, Edward Francis and Shirley B. Daniels, Elisa Goodman, for challenging me to apply to Radcliffe exactly 2 years ago and to leave the Radcliffe life. I have to thank Catherine Zucker, who's a PhD student in astronomy. She's also the PhD student of Elisa. Without her, most of the results you'll see today would have not been possible. So Catherine is a star beyond the astronomical, as you'll see later. Josh Spiegel, also a PhD student, Think Binary Research Group. I've been benefiting immensely from being close to them. I have to thank my Radcliffe research partners. They've been very helpful. And these were Owen Martin and Amish Nicholson. They're somewhere in the audience. I also want to thank Stefan Meingast back in Vienna and my research group. They are doing very, very well. In fact, they never did better than now that I'm here. I see my non-work related friends from a long, long time ago. Thanks for coming. And my new non-work related friends, thanks also for coming. I need to thank my family. Without you, this will not be possible. I know you're having a great time like I have. And I end by saying thank you to my fellow fellows. You are tremendous engines of creativity, and you've made my life over the last 6 months truly amazing. Okay, so my name is João Alves. I am a professor of astrophysics at the University of Vienna, and I came to Radcliffe to make a map. So my project is very simple. It's to take and use data from ground-based telescopes, these are telescopes on the surface of the Earth, space-based telescopes, and then construct the most accurate map of the gas distribution in the vicinity of the Sun. Not only the positions, but also the motions of this gas. I have found many things. I'll try to explain later why astronomers care about this map, but I have to tell you right now that while working on this map, I have found many things. And I found, together with my collaborators, and because of my collaborators here at Harvard, I found the largest coherent gas structure in the Milky Way. I found things I was not looking for, and I found things I didn't know I was looking for. So very briefly, what I want to do is share these results with you, explain how we got to them, and at the end, wonder about the meaning of, a possible meaning of these results. What you're seeing here is M83. I took this image a couple of years ago in the 2.2 meter in the Atacama Desert in Chile. And this is an image we will never have of our own galaxy. That's because we live inside a galaxy pretty much like this one, but we live inside it. We don't live far away from her. From the inside, it looks like this. It looks a bit complicated. You're looking at a summer night on some lake away from the city, and you can see clouds, dark clouds in the Milky Way in the background, but you don't get to see, how do they interact like you see in M83. So let's go back to M83. Let's zoom from this lake somewhere in New England and go back to M83. This is from Earth to M83. This is one of the closest galaxies to Earth, by the way, 15 billion light years away. And just by looking at the galaxy, you get to learn a lot. You see immediately these very red spots. These spots are the nurseries of stars. They are factories where stars are made. And then you have these dark lanes, and the dark lanes are the material that eventually will collapse to form new generations of stars. And you have these blue stars. The blue stars are baby stars. They're stars that are very, very young, weeks old, months old, assuming they live 80 years like us. Again, we will not have ever this view from our galaxy. Why is this important? Because we want to figure out how Meredith put it better than me, how stars are formed. This is really a story about star formation. Inside our galaxy, and this is now an all-sky image of our own sky, you get to see it like this. The way to see all-sky maps is you basically grab that side and wrap yourself around it. And this is a sphere around you, but we have to present it like this because we're using a flat screen. What you see is these dark lanes again now from inside, and you see all kinds of shapes. You have comet-shaped clouds, you have fuzz clouds, you have all kinds of interesting configurations. And what you don't see very clearly on this image is that these are the nearest nurseries of stars to Earth. And if we want to understand star formation, we have to use them. We have to look into them carefully and with the best telescopes, best instruments, to unlock this mystery. And why is it a mystery? I mean, don't we know by now how stars form? No, we don't. We have a very good roadmap. So it all starts with these big diffuse clouds like I showed you before. Inside these clouds, there comes these embryos. We call them dense cores. We don't know how they form, but they form in these very large clouds. These embryos eventually will collapse, will hatch. And as they collapse, they will form a disk. And this disk that you see here, edge on, is this dark band here, will feed a baby star in the very, very center. As time goes on, this disk will vanish, you have your baby star, and from the leftovers of that disk, planets like Earth would form. So what's wrong? Why don't we know, exactly how nature does it? Well, the problem is in the size scale, in the density scale. These are orders of magnitude. You don't have to know what an order of magnitude is, but I'll explain to you. So what nature does easily is take a cloud the size, say, of New England and collapse it to a star the size of a quarter. And this is the problem. We don't have computational power to take a cloud the size of New England, collapse it, and let it ignite as a star the size of a quarter. Here, the density scales even fail. So there are 10 orders of magnitude here, 25 here. They fail because the best vacuum we can do on Earth here is millions of times more dense than the interiors of clouds. But you get the picture. It's a problem of size and density scales. But we have a roadmap, and we don't think it's missing physics. We think the problem is getting the right recipe, which physics play an important role at which phase. To get an idea of how important star formation is perhaps the most favorite activity of this universe. It's like the secret sauce. What I'm showing you here is a simulation made by colleagues up the street at the observatory, and this is the age of the universe slowly moving on. And what you're looking at here is the formation of galaxies. And every group of points here are actually not one galaxy, but are clusters of galaxies. Now, for all the insight this gives, we don't know yet the secret sauce to star formation. So this can be off by a lot. And this is on a very large scale. So it is fundamental to understand star formation, to understand formation of galaxies, evolution of galaxies. On the very other end of the scale, you have planets. Remember, planets form on the disks that eventually dissipate and form little planets. Well, it's also a star formation process. It depends where your disk is. If it's next to a very bright star, it will be different than if it's in the middle of nowhere, quietly cooking planets. We have to understand the process of star formation to figure out how many planets are there, how nature builds planets, and how frequent they are. Great. So here's things you cannot do outside of our galaxy. And this is why we need a map, accurate map of our vicinity of our sun. To look at the stellar embryo, how does it look like? Well, here's one that I studied a while back. This is a stellar embryo. This is the last reservoir of gas that eventually will collapse. And we actually think It will be in the next 100,000 years if anyone wants to wait. So this little piece of cloud is entering this larger piece of cloud. And it's like the last drop that will make a stable configuration collapse. Only nearby, so this is in the optical, if you look at your eyes, you'll see it's very, very dark. The reason it's dark is because there's little particles of dust. And this particle of dust will create this effect called reddening. I'll talk about it later. You see that stars, normal stars look like this, but every star that goes through the cloud at the edges becomes red, just like the sunset is reddish. Through the center, there's too thick, there's too much dust for you to see the other side. And this is in the optical. If you put your infrared glasses, you get to see this. Now, what you have is all the stars that were on the other side of the cloud. These are stars they're not baby stars, they're not being formed. These are stars that are in the background. But then you have 1,000 measurements that will tell you very precisely what is the structure of this cloud. And this type of fine measurement can only be done in the very near molecular clouds, dark clouds. Another one is a fundamental problem in astrophysics. Turns out, by the way, that the ratio of massive stars to low mass stars is always the same no matter where you look. In our galaxy, in any corner of our galaxy, other galaxies. So this cloud here is that little spot over there. And here's a cloud full of stellar embryos, most of them not hatched yet. And what we did is, you can extract them the best way you can, and then you can just make an histogram of their masses. And when you do that, you get that, and tells you that, interestingly, the ratio of more massive embryos to less massive embryos is exactly like the ratio of high mass stars to low mass stars, suggesting that there might be a connection in there. Okay, I show you a lot about embryos. What about baby star, when they actually hatch? For that, I want to show you my favorite part of this, my favorite constellation, Orion, my favorite star formation region, and this is work that we did in Vienna a couple of years ago, and I'll show you the movie. The movie will have music, and it was made in Vienna, so it'll be Mozart. This is in Chile. This is the constellation of Orion. By the way, it's upside down, if anyone, for all the amateur astronomers in the audience, because this is Chile. This is the southern hemisphere. If you want to see Orion in a couple of hours, out of Byerly Hall, look over the building of art, and you'll see the big Orion there. It's fabulous in all kinds of dimensions. So let's go to Orion, and let's see baby stars. So here's the big constellation of Orion. All these stars are months old compared to the lifetime of us. But there's a nursery right there, the famous Orion Nebula, where it's the closest nursery forming all types of stars, high mass and low mass stars. You see all this red light. This is a sign of star formation. These are ionized gas by the young stars. Think of it of a very bad sunburn. And this is a survey we did in the infrared. This is a distribution of gas, the raw material. This is done using a technique that I developed with my PhD advisor, Charlie Lava. And this is then the vision, the survey we did in infrared with the 4-meter telescope in Chile. It's very, very large. It doesn't look like much here, but it is all kinds of, you have to take a piece at a time, different wavelengths. And now here's the baby stars. Here's the Orion Nebula in infrared. So you get to see thousands of baby stars, days old. And these are the massive stars that light up the entire nebula. Here's a very dark filament full of baby stars. And outflows, remember those jets that come out from stars? They're here. Another one there. Beautiful bubble around the massive star. Here's a beautiful jet coming from a source you cannot see even in infrared. It's here. It's shooting these jets left and right. Massive young star over there. Another embedded cluster, planets are forming around disks, around these baby stars. We found new embedded clusters in this cloud. The disk there. There's one there. And for me, what's amazing is just off the cloud, there's this gigantic cluster of galaxies far, far away. And every time you go deep with a modern telescope, you found new galaxies by the dozens. You can name them if you want. No, you cannot. Okay, so these are baby stars. So what's the plan now? The plan is to try to figure out how clouds come together, because if we know how clouds come together, that will tell us a lot about, these embryos form. Right now we have these snapshots and all we see is embryos. And it's hard to make, what we want is the movie. We want the cloud coming together, forming the embryos. For that, we have to measure motion in distance to these stars, to these clouds. Remember that they're all kind of 2D to us. It's very hard to measure distances. They're all on top of each other. Is this guy closer than this one? And why, it's this problem that we need to solve, is disentangle molecular clouds. And are they connected? Remember, until now, observations have been developed, the fields of view have been increasing, but typically we observe tiny little regions in these clouds to figure out, what their status is. Now, with the new generation of telescopes, you can take all of them. You have all sky observations. So to do that, you have to measure the distance and the motions to these nearby clouds. That's the goal of the project. Now, distances are very difficult to measure, and motions are essentially impossible to measure. It's a tough start. But let me start with motions. The problem with motions of clouds is that they're diffuse, and you have to wait millions of years for actually to have an idea of where the cloud is moving. Unlike stars, we are pinpoint sharp. You can easily measure their motion. So what are we going to do? We're going to try a trick. Instead of measuring the clouds, we're going to measure the babies. So we take all these babies, get a sample of babies across the nearby clouds, and we're going to observe them every 6 months. And we're doing that in Chile with a large public survey. And every 6 months, we're going to observe all the stellar nurseries that we can observe from the southern hemisphere. Basically, this just tells you that you cannot observe in the north if you're on the southern hemisphere. These are the regions we'll be mapping, and we're actually mapping at the moment. And we're mapping here in Paranal. This is in the middle of the Atacama Desert, and I just want to give you an idea of what is the life of the astronomer, or a day in the life of the astronomer. It's actually the night. Here's a time-lapse movie of a night in Paranal. So what you're seeing is there's all this light. This is the moon. The moon is there. The moon will set, and then you see it'll become very, very dark. And there's your beautiful Milky Way, the center going down there. Milky Way sets, and suddenly you might see a little bit of the LMC showing up there, and suddenly, boom, the sun shows up. And then we have to go to bed. Okay, so I told you that we're going to use the baby stars, the motions of the baby stars on this program, to measure the motion of the gas. Why is that? Because as I show you, they're very attached. You can use them as tracers of the movement of the clouds. Now, this is a work in progress, so I'll not show results from that because we're still observing. But I will talk about another technique at the end to measure these motions. Now, what about distances? Now, that is very, very hard too, but let's take the simplest method possible. Normally, the simplest method is the most powerful method, so geometry will do it. Now, we're going to measure distances using parallax. Parallax, you have everybody stick their finger up against the screen. Now, close your left eye, close your right eye. What happened to the finger? It moved. Okay. So imagine now it's the 1st of January, and that's your right eye. And let's see what happened to a star that's only a light year away compared to stars far, far away. So this is what we'll see. As the Earth goes around, and when it's July, your star moves in this funny shape. Now, if your star is further away, you'll immediately can figure out that this circle will be much smaller. There it is. Okay? So in other ways, let's assume that all stars are static in the sky, and the sun and the Earth goes around the sun every year. This is what would have happened. Nearby stars will make larger circles. Far away stars, like this little blue guy there, barely moves because they're far, far away. Okay, so using parallax you'll be able to tell the distance to this star by how much it rotates in the sky, because we're measuring it over the year, and we want to observe the orbit of your star. Now, stars are not static, they move. And when they move, then this changes a little bit into that. There's one guy very, very fast. So they don't really do circles. They do funny shapes. Okay, and it depends in all kinds of funny shapes. This one is like this, but if you look at other stars, look at that guy, kind of then stops and goes another direction. So every star has a funny shape as it moves across, because of this parallax effect. Now, this is very important, but all you have to do is to measure this line, and then this line will tell you two things. It will tell you the distance to the star, and it tell you how much the star moved on the plane of the sky, the motion of the star. Now, that's great, that's so simple, so what's the problem? Well, the problem is this is exaggerated, this movement, by about 1 million times. So what you have to measure is this, but with the precision of a quarter, the same quarter, on the moon. Okay, so you have to be able to see the width of a quarter of the moon to measure these kinds of motions. To do that, you better go to a very stable place with no atmosphere, no kids, nothing. And you do that in space. And this is then what the Gaia mission that Meredith talked about. This is an astromagnetic satellite that was just designed to do what I just showed you, to measure these weird patterns of stars. And it will measure 1 billion of them. 1 billion. 1 billion. It's unbelievable. This is a telescope that I think will change the face of astrophysics over the next decade. It's already changing. It's inside this pod here, and let's see a little movie as the satellite gets launched from the French Guiana. This is a European mission. Many, many people worked here for years on this mission. And this is all a very tense moment, launching, because everything can go wrong very fast. It's in French because it's more stylish to say it in French. And there it goes. And then we have to track it. It sends data to us. We have to track it with the antenna like this one. And what it does really in space, there's an animation, is this. Here's Gaia. And all it does is this umbrella, it faces towards the sun to protect it from heat. And all you have is these two telescopes right there, very strange looking telescopes, and it just continually rotates. And the mission takes 5 years. So it goes 5 times around the sun. Why do you need so much? Because remember, you have to figure out that weird pattern. You have to figure out that with a pattern with measurements. So we have to fit then that your data of the telescope is scanning. You have to fit it for every star. You have to derive that strange pattern. So we have to observe about 70 times every star in the sky. So this satellite is still observing. Will still observe is finishing its first 5 years. And this is how a lot of the results I'll show you now are possible. It's really because of this development of technology. All right, so I said I wanted to make a map of the local neighborhood. What do we know about it? I'm sure we know a lot about it. Yeah, we do. We know about it since 150 years ago. This is Jeremy Gould, was a student here at Harvard, and then he found the observatory in Argentina. He was the founder of the Astronomical Journal, and he was mesmerized by this circle of stars that was not on the plane of the galaxy, but it was kind of off the plane. And first he says he was surprised that no one knew about this, and then he realized that Sir John Herschel, so the son of William Herschel, already mentioned it, and then a summary is here, and he's still shocked that yet he does not appear to have recognized the fact that this zone of bright stars may be traced through the entire circuit of the heavens, forming a great circle as well defined as that of the galaxy itself. How strange, a ring inside the galaxy. This is what he's talking about. This is, again, the center of our galaxies. You see beautiful, beautiful clouds. But what he's talking about is this band of bright stars. And this band goes up all the way and then down, and then imagine goes around, and it does like a ring, a band about it. Another way like this. So again, remember, you're allowed to wrap around. So this point here touches this point there. And the previous satellite gave a lot of power to this idea. So this is 150 years ago. And if you look at the distribution of young stars, as we knew them before Gaia, they kind of looks like a ring, and it looks like it's inclined. You see? And this is something that John Herschel noticed, that this disk is inclined by about 20 degrees from the plane of the Milky Way. By the way, these are XYZ plots. It's very simple. It's like a box. XY means you're looking down on the box. ZX means you take the box and look this side, and then you rotate the box, and that's YZ. So this is from above, you see these two lines, but if you see from the side, if you could look from here, now this is the plane of the galaxy, and then you see this structure that we thought was the Gould Belt. A lot of papers went into this. Then we thought that this is a description of what the Gould Belt is. This is Orion, my lovely Orion, Scosan. You'll be hearing a lot about this. These are the nearby complexes, and there's this ring. And we never knew why the ring was there. Lots of models have been proposed to explain this ring. It's not only a ring, it seems like it's been rotating, and not only rotating, it's expanding. And it feeds a lot of papers, and this is what we think the local neighborhood looks like, this vicinity of the sun. Even as late as last year, with Gaia data, this is the best model of the ring. So now again, you're seeing the top down on the galaxy, and you see the ring like this. You're seeing now from the side, and it looks like it's inclined, and you see from the other side of the box, and it's also inclined. And the arrows mean velocity, and it looks like that it's an expanding ring, like many people said before. Great, so let's try to find this ring. This is where I found things I was not looking for. This is through the work of wonderful Catherine. I'll try to explain very briefly what we did. So what we do now remember, we have wonderful distances to these clouds. So to these stars, what you're going to do, we want distance to clouds. And what you're going to do is you take a region towards the cloud, and then you just basically count. So to one of these regions, you count, remember reddening? The fact that stars get red like sunsets as they go on the back of clouds was the same. We're going to use that to determine the distance. So from here to Orion, the first stars don't have any reddening, so it means they're in front of it. But suddenly there's a big jump, and these are the stars that are on the back of Orion. So then the distance to Orion is simply where this jump takes place. So this is what we did. We did this for the entire Gould's belt, and expecting to see a ring in high definition. And this is what we got. This doesn't look like a ring. In fact, that's the Gould's belt. What's happening? What gives? We have now the best distances to these clouds. We should be seeing the disk, the famous Gould's belt, in high definition and try to figure out how it's formed and test it with models, but we got something completely different. And this is very straight feature that's very, very long. It's almost 6,000 light years. And it gets even more complicated because I'm now showing the top of the box. So we're looking down on the plane of the galaxy. Now I'm showing you from the side. And when you look from the side, you get that. It's undulating. Okay, so it's not even on the plane. It starts on the plane, it goes down, and then it comes up again. This is completely new. And I'm going to show you, thanks to Catherine, what it looks like in 3D. There it is. What is this? Look how nice, you can align the entire distribution. And there it is. It kind of starts at the plane at 0, goes down 600 light years, and goes up again, and it looks like it's curving down. It's clearly not a disk, and this is then from the work of Josh. Here's the same, but through the eyes of a statistician. Basically, I do not know anything. I let the data speak to me and tell me what's there. And the data tells you, yes, there is something, and it's red. And it's this wave structure that we talk about. Oh, yeah, what about the ring? What about Gould's belt? Not a chance. There's nothing there. In fact, the ring was defined using these regions, Scosan and Orion. And it had to pass through this one because this is how it was defined. And now that we have these wonderful distances, you look close, nothing fits in this ring except for what you're forced to fit. Instead, what you have is this very long structure that we have no idea what it is. It is strange because it contains most of the nurseries that we knew of. Remember from the beginning, everybody says, what's in front, what's not in front? Well, they're all aligned. Why? So because it's the first time we find such a large structure, we decided to call it the Radcliffe wave. A tiny homage to the women computers from Harvard, one in particular, Henrietta Leavitt, and to this institution and to my fellow fellows. So this is the largest coherent structure in the Milky Way, 6,000 light years. It's a family of clouds. What we used to call a giant molecular cloud, Orion, these nurseries, they're all pearls on this necklace. It's a very long necklace that starts somewhere here, goes back and up into the plane. If you see it from top, again, it's very, very, very narrow. If you see it from the side, it gets this very sinusoidal-like function. Again, I mentioned it's very, very long. The mass is 2 million 2 million times the mass of the sun. And it's a very, very, very strange aspect ratio. We don't know things so stretched in nearby galaxies. So let me give you a little GLUE demo. GLUE is the software being developed in a group of Elisa Goodman. And again, thank you, Catherine. What I'm doing here, and this was actually a lot of fun, because when we were just talking about this, when we found this, and I called Alyssa and I said, oh yeah, there's this nice result here that you have to see. And she says, oh, come over to my office and let's have some Indian food. And I don't think she realized what I was talking about until she said, oh, but we have to, I showed it to her, but you have to use this software that we've been developing. And this software allows you to drop your data on this model of what we think is the Milky Way. Now, this is a model. This is not the real Milky Way, but it's a guided, it's an informed model of the Milky Way, formed by astronomers. And what was strange was we just dropped the data on this software, and you see this, this no ring, no ring, but you see this very long elongation. So one of the problems I had with this very straight, it was too long. Normally, you look in nearby galaxies, you don't find these immense trains of clouds. They're much, much smaller. So why are we special? No, we're not special, but And let me show you what it looks like. You can interact like this. The galaxy is slightly thicker than this. This is obviously just an image. And then you can see, we center on the sun. Where's the sun? Oh, there it is. Where are we? 1, 2, 3. We're there. That's us. Let's go back. These are the nearby stars. If you go back, here's our beautiful Radcliffe wave. Great. So, Mr. Gould, I'm sorry. There is no ring. So we are now free from 150 years of constriction from this ring. No, it's not so bad. This needs to be validated. So a lot of people have done careers on the Gould belt. So don't take this with a grain of salt. I don't think we looked, there's no way we're wrong. So I'm pretty sure this is the end of the Gould's belt. Remember the 20 degrees? The magic 20 degrees that no one knows where this comes from? Well, the 20 degrees is just this. As the wave crosses the plane, has about 20 degrees. And what we're seeing there on this lane are actually the stars that are missing between Orion and Cepheus, this matter, basically the stars here. This part is more evolved than this part, so the stars here belong to this ring here, to this wave there. The other one, this part is cosine, and we think it's something similar to the Radcliffe wave. In fact, we think more than similar. Let me just show you soon. So, oh yeah, what about this 2018 paper? I mean, can they be wrong? They use Gaia data. They are not wrong. The model is wrong. So this part, these clouds are moving somewhere. These clouds, these are part of the Radcliffe wave. And look how they move in the same direction. And what's happening is, that's the Radcliffe wave. That's the other one that contains this region's cosine. And what's happening is that they're moving away from each other. And because we're sitting here in the center, we think that we're seeing that we are inside a ring, and the ring is falling apart. There is no ring. There's only the Radcliffe wave. Okay, now comes the kinematics. Thanks you, Owen Martin, for this. And this is now, when you start showing data that is still inside software, it means that it's not ready yet. What I'm showing you here is that the other regions, cosine, the ones that's not part of the Radcliffe wave. Now, because we have the velocity of the stars, these are just the baby stars. Because we have the velocity of the stars, we know the mass of the galaxy, we know the model of the galaxy, we can do something amazing. We can go back in time. And this is what we've done. This is now, here's the time. Let's go back 20 million years. As we go back in time, you'll see that the entire association of young stars become a very elongated structure. That's about the age of the stars, means that this is when they were born, and look how straight. They follow the same line. In fact, they are both above the plane of the Milky Way. And remember that we're going back, so the expanding region now is a contracting, these two lanes are actually getting together. So what's happening is, this part of this star-forming region and all the gas associated with it, actually, if we go back 20 million years, so now this is our best guess, and this is very rough, okay? This is our best guess of the positions and velocities of the Radcliffe wave, and this is what I just showed you. So now, what I was showing before was just the stars. I'm just showing averages of stars, and they align. So essentially, they're branching out. So sometime 20 million years ago, there was a branch out of the Radcliffe wave was cosine branched out of the Radcliffe wave. Now let me go through 20 million years to the future and another 20 million years. And the way to look at this is, look at us, we're in the center. And the way to look at it is that we're kind of in a spacecraft called Earth, and we're going to go through, the galaxy will move, but we're going to go through the Radcliffe wave. So 16 million years ago, the sun passed very close to cosine. Look at that. And this is about now. No. Wrong button. This is the Radcliffe wave, by the way, and about 18 million years ago, we'll be surfing the Radcliffe wave. We're going to cross the sun in 18 million years, we'll cross the Radcliffe wave, and we'll continue its journey through the galaxy. Because the sun is faster, all these baby stars we left behind the sun. Okay, so we know a lot already, and there's much more to be done. But I want you to introduce you to the new local neighborhood. There is no ring, but instead you have these long families, these corridors of gas, and let me now give you an impression of the Radcliffe wave. So it starts somewhere there, and it's far away, and then it becomes closer and closer and closer. Now remember, that point goes to that point over there, they touch, and then goes up, crosses the plane, goes up again, and then down. But that is the Radcliffe wave seen from Earth. The other one, the one that we believe branched off the Radcliffe wave 20 million years ago, it's this one. It's all these clouds here, and they kind of go to the plane there. And the stars that I show you on this visualization, all the baby stars are inside this area. So this is welcome to the new local neighborhood. Meet the neighbors. The neighbors are the same, but the structure is completely different. So what does it all mean? We don't know yet, because we're not even sure. I mean, like, it was fantastic that you said that I tend to find things that are hiding in plain sight. We've been sitting next to a giant for millions of years and never realized. So it's true. I don't know why, but I do this. The sun is somewhere here. This is not our galaxy. This is another galaxy. And what might be happening is, for those in the audience that know the local arm, what might happen is the Radcliffe wave is just a spurring off the local arm. And you do find these very, very long structures. Finally, the next couple of minutes, I want to talk about something different. Things I found that I didn't know I was looking for. Last October, we had this exhibition at Byerly Hall by a visual artist called Anna von Mertens. I was mesmerized by the work of Anna. I was by the method. She basically researched on the life of Henrietta Leavitt, who's one of the computers. And all she does condenses months of research into a quilt. And this is one of the quilts. What's interesting here is that this is October. In October, we have no clue about the Radcliffe wave. Okay, and now, do you see what I see here? The Radcliffe wave is just a stitch on the work of Anna von Mertens. Okay, was I influenced by the work? I don't know. Maybe I was. I think I was. In the meanwhile, I had the opportunity to talk to Anna and to compare the work of the astronomer versus the work of the visual artist. And I was mesmerized to find that at the very bottom, we're doing the same thing. We're doing visual maps. And we're using maps to navigate the unknown, to make connections between clouds, in my case. In the end, we're using maps to find our place in the universe. So I thought about it and tried to find the words to explain this comparison between a visual artist and an astronomer, and I didn't find them. Maybe there are words, maybe Anna knows the words, maybe some of you know the words. And I thought it probably is because we have been life forms seeing for millions of years, and we only been speaking and using words for 100,000 years. Maybe there are no words yet. Or maybe it's much simpler than that. It's just education. You know, our education system, at least in Europe, and I think the same here, forces kids to choose in a very early age, to use one side of the brain, either creative or the analytical, and it's a very biased system. Okay, maybe this explains why scientists have a hard time thinking creatively like visual artists. In true Radcliffe spirit, I think I can say that I now see better because of the work of Anna. And I don't think astronomers can see better than visual artists. I think it's actually the opposite. And I think there's an immense potential to teach astronomers how to see better through interaction with visual arts. So this is my Radcliffe lesson. One can see more. The same is true for my fellow fellows. So the same parallels that I just mentioned apply across musicians and social sciences and psychologists and poets and mathematicians, all in the room, social science, writers, movie makers, biologists, and even chemists. Sorry. We are all making maps. So what have I told you? I told you that we are on the brink of discovery, that there is an entire Milky Way full of surprises. I just told you that we've been sitting next to a giant, and we didn't even realize. So we, Homo sapiens, have been around 3 days in the Milky Way year. Milky Way year is one rotation around the Milky Way. We just started. Okay, so there's many, many more adventures to enjoy. And it's basically, let me summarize again. I came to Radcliffe to make a map. I did find, while working on this map, I did find many things. I found things I was not looking for. And I found things I didn't know I was looking for. Thank you.